Hey guys, so real quick, I wanted to go over enzyme function. In a bit of a rush here, so forgive the weird lighting, the weird angles. Here we go. So enzymes are proteins that function as catalysts within living things. A catalyst is a molecule that speeds up the rate of a reaction without itself being used during that reaction. Okay. And so we have our protein, the enzyme here, and then we have the substrates, which are the molecules that are involved in the reaction that the enzyme is speeding up. Okay? And so there are going to be regions of the enzyme that have particular shapes that match the particular shapes of the molecules involved in the reaction. Yeah. And so if you look more closely at the enzyme, in those domains that are interacting with these substrates, there will be free R groups that have properties that are attractive to the molecule. Right? And so here I've represented that with light blue R groups. Let's say they're polar R groups. Okay? The molecule would have a region that is polar. Right? So this polarity here would be attracted to this polarity here. And whereas, let's say the purple one is nonpolar, these R groups are nonpolar, it'll be attracted to the substrate's nonpolar regions. Okay? So both the shape and the chemical properties are complementary. So when the substrate bumps into the enzyme, this substrate here is going to fit in nicely into this shape. And then the enzyme itself is going to slightly change shape to grab and hold on to that molecule. So once a molecule locks into that spot, the protein holds onto it and it floats around hanging onto this first substrate. Yeah. Eventually, the protein, the enzyme, will bump into the second substrate, okay, and grab that as well. Yeah. And so it grabs both of the substrates and it pushes them together, right, and it makes the reaction occur. So if this is substrate A and this is substrate B, the enzyme puts them together, chemical reaction occurs, and we get molecule AB. Okay. And so when we have enzymes building molecules, that is anabolic. This is the building of new molecules. Okay. So here's the enzyme completely unchanged, ready to go find more substrates, build more molecules, and here's our new molecule AB. Enzymes can also work catabolically, which is to say that they can break down molecules into smaller pieces. So here I have a big molecule, let's call it CD. Okay. It has regions that are shaped to fit into these pieces of the enzyme. They have complementary chemical properties as well. So when this bumps into this, the enzyme grabs it, it holds on. Okay. And then the enzyme, once it has hold of that molecule, will change shape and break apart that molecule. Okay. And so here I have the enzyme, again, unchanged, and now I have molecule C and molecule D. Okay. At an AP level, okay, it's important to understand how the enzymes are actually making the chemical reactions occur. Because these are chemical reactions that would, on their own, in nature, happen. Right? The enzyme isn't necessary for it to occur, but it speeds up the rate at which it occurs immensely. Okay. And so in order to understand that, we have to understand how chemical reactions occur in general. Right? And so if you have a molecule, the different elements within the molecule aren't stuck in one place, right? They're moving, like they can vibrate. Right? And so they're not always exactly in this position. Sometimes they tweak a little bit, sometimes they move together, sometimes they move apart. Right? But there is a preferred state for that molecule. Right? And typically it's where the elements all have the most space around them. Because each element's electrons are bumping into the other element's electrons, and that's not good for energy. Right? So if each element gets its own space, the molecule is stable, energetically speaking. Right? And so here you can see in this molecule, everything is all spread out nice and evenly, and this is the energetically preferable state. This version of the molecule is not very reactive. It's stable, it wants to stay the way it is, it's cool. If other molecules come along and engage with it, it's going to be like, I'm all set, get out of here. Okay. However, from time to time, this molecule might look like this. Right? So this arm right here has bounced up a little bit. So it's vibrated up. It happens. right? These bonds are just shared electrons, so they can move around. And in this state, this molecule is not super happy, right? It's not as stable as it was up here. And so if another molecule with favorable properties comes along and happens to bump into this molecule while this molecule is in this state, there's potential for chemical reactions to occur. Because this guy is not super happy the way he is. So he's like, well, I'm not happy and you look cool. Let's do something about it. Yeah? And so this is more conducive to the reaction. Another way to think of it is if you think of it on a physical level, this is the stable state. If another molecule comes along, there's no way for it to access the reaction point. So the reaction point is going to be in here. It can't get there. Right? And if they can't bump, they can't react. When it's in the unfavorable conformation, the molecule that wants to react comes along and it can access that reaction point. So like this element would have some properties that are attractive to this element, and they might exchange pieces, and maybe he gets stuck on here and this guy gets thrown away. That might be what happens. Okay? And so at any given point in time, the molecule can be in this conformation, depending on how much energy is around, right? But it prefers this conformation. The more energy you put into the system, the more time that the molecule is going to spend in this conformation. And so the more readily it will react. Right? So adding energy increases that uncomfortable conformation's existence. Yeah? And it also increases the rate at which molecules are bumping into each other. So it makes reactions occur more quickly. So the enzymes force the molecules into their uncomfortable conformations. When they're in the enzyme, they're forced to be in that uncomfortable shape. Okay? And so they're always like that, and so they're much more easily reactive. It also takes out the random nature in the direction in which the molecules are hitting each other. Right? And so if the opening is here and the new molecule wants to react like this, okay, if they bump into each other like this, that's not going to work. If they bump into each other like this, that's not going to work. So the enzyme makes sure that everything lines up and the reaction sites are always touching each other, and that the molecule is always in the conformation that's favorable for reaction. Okay. So here's a chart. Right? In order for a reaction to occur, you need to be going to a more comfortable state. Okay? So if A and B individually are at this energy level because they're comfortable, they don't want to be AB because they're already comfortable the way they are. Okay? And so to make this reaction occur, we add energy, right? And that puts them into those uncomfortable states, which is way up here in the energy level. Okay? And then when they're way up here, they're like, this is not cool. I'd rather be AB. So they'll become AB, and then they'll be stable at this energy level. Okay? So you have to get to a high energy level to come down to make a chemical reaction occur. By adding an enzyme, okay, we actually reduce the amount of energy needed, okay, to make that happen. And by reducing the amount of energy we need to make that happen, we reduce the time it takes for that reaction to occur. And that's how enzymes speed up reactions. Cool. That's it. Bye.